Hi everyone, welcome to the video series on vectorization in natural language processing. It is a required step in text preprocessing. As you know, computers require numerical data for processing. Vectorization transforms text data such as words or documents, PDF, articles, text data into numerical vectors and thereby enabling the mathematical operations like machine learning, for example. Vectorization techniques like word embedding or TF-IDF, they capture semantic relationship between the words as well, and thereby providing a more meaningful representation of the language to the machine learning. This also enables the NLP models to understand the contextual nuances and similarity between the documents or PDF or articles, and similarities in the meaning, enhancing their abilities to perform the tasks like sentiment analysis, text classification, or language generation. As in other videos of mine, each topic here will consist of detailed conceptual walkthrough, mathematical intuitions if required. I'll try to keep it at a high level so that everyone can understand, and the use cases and implementation using Python, scikit-learn, TensorFlow, or PyTorch in some cases. So the topics that I'll be covering here would be the variety of vectorization and embedding techniques. To start with, we'll talk about the bag of words and count vectorization. Each of these vectorization or embedding method, I'll be showing you the Python demo on text classification or sentiment analysis for using IMDb dataset. So what is vectorization? It is a transformation of text data into number format, essentially a bridge between the human readable or human provided text data to a machine readable data. Vectorization is a mathematical way to transform. At the same time, this is also an art of choosing the right vectorizer for your data. Let's take an example. Let's say your input data consists of three records, document 1, 2, 3, and these are your sentences. We will first tokenize the input document 1, 2, 3 into individual words. For example, here machine learning is fascinating. And so the word machine is one unit, learning is another unit, so on and so forth. In the next step, what we're going to do is combine or take all of the tokens from the previous step and build a vocabulary of unique words. Now, by using this unique word representation, we are going to convert our data or input data into a number format called vector. So let me explain what this actually means is, let's say the word machine, if that word appears in the document one time, so you just put one here. Let's say the word fascinating, does it appear in this document? No, it doesn't. So we just put a 0 here. And likewise, we're going to fill up all this. If a particular word, let's say natural, appears in document number 3 5 times, so that would be made 5 here. So this is called the count representation method. Now, in contrast, embedding is slightly different. The purpose is the same, to give you a vector representation of input data, but in this case, the embedding, we are going to have a continuous vector space. So what's the difference? Let's take a look at the previous one. Here you have the vector representation of frequencies, and most of these values are 0, 0, 0. And some places you would have like 1, 2, 3, 10. Those are frequencies. In contrast, the embeddings will be continuous. That means we will not have the count. We will rather have a continuous value like 0.47, 0.37, zero point 0.1, and how many, that is the user definable. So let's say we define the length of the vector 50. So this will be consisting of 50 values, and those values are float, and this is called embedding method. So embedding method, addresses the problem of sparsity where you have lots of zeros. You will not get the problem of sparsity in the embedding cases. And embeddings also capture semantic relations between the words. For example, if I say I'm sitting at the bank or I'm banking on you. These two words or the word or like bank have a different meaning, and that can be captured by embeddings much better than the vector method that I showed you earlier. So let's take an example of a the embedding. Imagine we have a two-dimension embedding space and the words are like king, queen, man, and a woman, and this is represented like zero point 0.8, zero point 0.6, and so on and so forth arbitrarily. And if I plot these four words in terms of the coordinates, then they might appear like this. The intuition is that the king and a man, the embeddings are pretty close. Similarly, woman and a king, woman and a queen are pretty close. So how is that? Let's take a look at this the vector for woman and vector for queen. They have a smaller angle. Similarly, the vector for man and a vector for king, that has a smaller angle. But if you look at the man and a woman, that angle is larger. So the method that we call embedding, they give you a better semantic understanding of the tokens or the word or the sentences or paragraph or the document. So let's move on. Um, So the bag of word or a count representation is simply the representing your input data in terms of frequency. So let's take a look at it. It's one of the simplest method of vectorization. Here the input data or record is represented using frequency. So value in each of the element, that represents how many times that word is appearing in that document. So let's take an example here. Again, let's say my bag of word consists of these 5 words, and my document one is A and E. So how do I represent the A and E? A is here, the first position, so that gets a 1. And B, C, D are not in the document, so 0, 0, 0. And E is here, so we will make it 1. So that's the vector representation for document 1. So the intuition behind the bag of word, let's say this is my PDF, and from this PDF, let's generate the unique set of tokens and sort them alphabetically, for example, here, and then associate some numbers like index 0, 1, 2, 3, 4 for each of the words here. Imagine the input. So this is called bag of word here. Input data is AI wins, always wins. So look for the word AI in your bag of word that appears in the first position. So that will become 1. Wins is appearing somewhere. Wins is appearing maybe somewhere. Yeah, here 1051. So that win is twice. So that count is 2. And likewise for the rest of the word. And eventually you will get a vector representation. The length of the vector representation would be the length of the bag of word, which is 10,000 in this case. So why we need a corpus? The corpus means the comprehensive set of data. In order to build a text classification model or any NLP application, our corpus should be comprehensive. That means it should represent almost all types of text data that we deal with in that particular task or in that particular project. So the corpus is also essential to carry out statistical or exploratory text analysis, for example, collocations or n-gram analysis. Let's take one more example here of bag of word. So we have document 1, document 2, and we form the vocabulary, which is a unique set of words or tokens from the input data. And then we represent the input data using the bag of word that we have just formed, and then put the frequency of the word as many times that word appears in the input document. Some of the key characteristics essential to understand some of the limitations and the characteristics of the count method or bag of word method. It is based on word frequency, which means every word is counted how many times it appears in the input document. If it is appearing 10 times, the vector representation in that position would be 10. Now, the variation to the count is a binary where you don't want the frequency, you just want the reflection of the fact that the word is actually appearing. It doesn't matter how many times. If it appears, then make a 1. If it doesn't appear, make it 0. So that's called binary representation. Order is ignored because the way the sentences are given as input to the machine learning model, let's say logistic regression, it is not the way we will feed the vector, because the vector will be in terms of the bag of words. So the order of words in a document is not preserved. So that means some loss of information as well. Now, vocabulary set is a predefined vocabulary set. That means if you have 100,000 input data, let's say PDF, so however many unique set of words that you have, that constitutes or defines the size of vocabulary. Sparse representation is one of the problem with count or BOW method, and that makes the model computationally very heavy and also sometimes inefficient in terms of the generalization ability of the model. Scalability is also a problem with the count vectors because the length of the vector typically is very, very high, 100,000, 200,000, and 300,000. That size of vector in mathematics is quite difficult to process. At the same time, BOW is scalable to large data sets. So it doesn't matter, you just push the data in and you can build the vocabulary. So there are some advantages in terms of large data sets, but disadvantages are also there in terms of a large vector size. Text processing or pre-processing is one of the important steps here. make we need to make sure the data is representative. It doesn't have unwanted or irrelevant or noisy tokens or the words. In order to get a quality representation of the input data, text pre-processing typically takes 30 to 40% of your machine learning project time. Some more key characteristics: document similarity, bag of word. Since it is a vector representation, you can perform tasks like document similarity, like if one PDF is similar to the other or not. Since we are having a vector representation, it is much easier to compute the cosine similarity between the vectors. Dimensionality can also be very, very high. As I mentioned earlier, size of the data, size of the corpus determines the size of the vector. High dimensionality can result in requirement for a lot of computational resources. Some more key characteristics: the bag of word does not always mean only one word bag. It can be 2 words or 3 words. For example, New York is one word. So we need to again do some pre-processing and make sure the frequently bigrams or frequently used bigrams and frequently used trigrams or fourgrams are extracted and kept in the bag of word like one unit. Application flexibility. It is quite flexible. You can use the bag of word representation for almost any most of the NLP tasks here. It serves as a baseline model. That means if you get an accuracy of 60% with BOW method, then if you try some advanced methods, let's say neural nets or some advanced embedding, you should aim to get a better performance. Final illustration on bag of words, document 1, 2, 3 as the input document. Step by step, first we tokenize each of the input document are going to be tokenized, and then prepare the bag of word or vocabulary, which is a unique set of all the tokens in your input data. Use the bag of word representation to create the vectors for input data like document 1, 2, 3, and these are your vector representation. Now the explanation is already I have provided, is simply based on frequency for each of the document 1, 2, 3. You look for the token and you find out how many times that word is appearing and put that count. Let's look at the Count Vectorizer implementation. It has two flavors, the frequency and the binary. Frequency means the count, binary means we don't care about the frequency. As long as the word is present, we will mark it as 1, and if it is not present in the bag of word, we'll mark it 0. So the Count Vectorizer essentially starts with a collection of the text document, convert the or extract the unique token set, and that is called bag of word. Use the bag of word to represent your input data into the format of a vector. Input is typically a file in Count Vectorizer. We'll see in the Python code how we provide an external file as the input here. You can also go for lower casing. Let's say, before you apply vectorization, you don't care about, capital letters or something like that. Everything can be converted to lowercase. Then you can opt for lower casing, but this is not advisable. Many times you would like to preserve the casing, so you should turn this off. Token is the way to tell the count vectorizer what is token. Token of length of 1 character, 2 character, 3 character, or ignore anything which is less than 3 characters. So you can provide regular expression to guide the count vectorizer to consider the length of the token to be minimum 4 or 5, or it could be slightly complex regular expression as well. This is very, very handy. Stop words, you can maintain your stop words and build a list of stop words, and you tell Count Vectorizer to ignore those stop words from the training or testing data. Some more parameters, n-gram range, like I mentioned, default is 1 word as a bag of word, but you can go for 1 word or 2 words. For example, here, if you mention 1 comma 2, then it will be a set of 1 word plus the set of 2 words, means 2 successive words. You can also go for 1 comma 3. In that case, it would be set of unigram, bigram, and trigram. Analyzer is a way to tell to process the data by word or character. Generally, it is word in most cases. Maximum document frequency is telling how many times that the token is present in the input document. Let's say a token is present in all of the document. In that case, it's going to be 100%. But if you want to limit it, you want to say that, okay, if the token is, let's say, should be maximum 90%, then you pass 0.9 here. And similarly, if you want to ensure the token should be at least 5% in all of the document, so 5% of the total number of documents. Let's say you have 100 documents and the token should be in at least 5 of them. So it should be 0.05. If you want to limit the max features or max number of tokens or the words, you can also specify that limit here. Default is none. That means as many tokens as you have in the data. So the use case for Count Vectorizer, you can apply these count vectors for text classification purposes, clustering, information retrieval, and keyword extraction, and so on and so forth. In this demo, after this, I'm going to show you a demo using Count Vectorizer and perform text classification on a movie review data set. Now, some of the limitations of the bag of word or the count method. Count vector method treats each document as a bag of word. It does not consider the order in which the words are used, and that means the loss of information. It is also fixed size vocabulary. That means a new word in the test data or unseen data, it won't be represented because it is not as part of the training set. It is also sensitive to stop words, so we need to do a careful analysis as to whether we need to remove those stop words from the training set. Count vectors, they do not differentiate in terms of the weightage of the tokens. It provides equal importance to all the words. Only way to differentiate is higher the frequency, higher the weightage. Sometimes that may not be the right approach, and we have variation to count vectorizer called TF-IDF, which I'm going to be covering in the next video, how to use or what exactly TF-IDF does and how does it address the problem of equal importance. Sparsity is a problem with the count vectorizer as well as TF-IDF vectorizer. Most of the values in the vector will be zero, and that is a problem in many of the machine learning models. Contextual understanding is quite limited with a bag of word. The reason is it does not keep or preserve the order in which the words are coming or processed, and that means it's not suitable for semantic analysis. And we will look at how the advanced embeddings like word2vec and glove and bird actually help. Coming to the demo using IMDb dataset for text classification. This is going to be the demo that I'll be showing you in a while. Let's take a look at this simple demo of text classification using movie review data. It's called IMDb dataset. I have already pre-processed the data. I'll be providing the dataset in the description below and also the code here. This movie reviews data has 50,000 samples. They have been categorized into two classes, positive review and a negative review. So I'm not going to be executing each of the step, but I'll rather show you the outcome here. We'll focus on the last column, which is cleaned text column, which I have cleaned after doing pre-processing here. You can compare the original review data and the clean data here. It is actually pre-processed. So let's take a look at what we do in terms of vectorization. So this is my data. We'll do a train test split for evaluating the performance of the machine learning model. Train a count vectorizer. So the count vectorizer method is called count vectorizer, part of the feature extraction module of scikit-learn. Initiate your count vectorizer, fit and transform. So when you fit and transform is going to build the vectorizer with a bag of word, and transform will transform the training data into the vector. So this is called our document to term matrix. Similarly, we need to do it for the test data, but in case of test data, we don't fit it. We just convert the test data based on the vectorizer that we trained in the previous step. Let's use the machine learning model naive Bayes, multinomial naive Bayes, pretty good with text data, especially the data where you have count, frequencies, and the discrete value. Multinomial naive Bayes performs very well. So set up your multinomial naive Bayes and train the model and predict. Let's do some evaluation, and is about 84%, which is pretty nice as a first attempt. But there are errors here. If you look at it, 600 is the number of false positive. That means the negative review has been predicted as positive. That means there are some issues with the way we have pre-processed the data. Take a look at the false positive for exploratory purposes here. And let's do a predict proba of the testing sample. As you notice here, it is very discreetly saying the first sample is a class of 1, second one is also class of 1, third one is a class of 0, and so on and so forth. Now we'll use the predict proba to generate the ROC AUC score or AUC score, which is also pretty nice here, 0.91. Plot the ROC curve by using the ROC curve method from metric package of scikit-learn, and this is also quite pretty good actually here as a first attempt. Let's take a look at the top words in the positive and negative reviews. So I'm going to be using word cloud for positive data. Take a look at the positive data. It really doesn't tell you much in terms of the words, why the word time should contribute to the positive review. Similarly, for negative also, why the word movie should contribute to being classified as negative. That means it gives enough indication that we have to perform more stringent pre-processing or stop word removal of the data or tokens. So, if you look at the high frequency word, these are definitely not the words that you should consider, contributing to class prediction like positive and negative. In fact, the words in the positive and the negative, they are pretty common here. So this gives you enough indication that these words can be actually removed. So some of the suggestions here, many words are common between positive and negative. Many top words, they look like stop words, so good candidates for removal. Some more pre-processing may be advisable here, or choice of a better vectorizer. In the next module or next video, I'll talk about TF-IDF, and I'll show you some how TF-IDF can give you slight improvement here. Better choice would be to use a dense representation, which is like, BERT embedding or GLOVE or FastX or ELMO type of embedding. I hope this demo was interesting. We'll see you in the next video. Next video is going to be on TF-IDF. Yeah, we just concluded the implementation code walkthrough of text classification using Count Vectorizer. Next, I'll be talking about, in a new video, I'll be talking about TF-IDF. Thank you all. We'll see you in the next video.